Okay, so now we're going to take a look at some additional uh, theories of bonding. Thus far, we've looked at the Lewis theory of bonding, which involved drawing Lewis structures, which gave us a basic idea of how the atoms were laid out and how they were connected in a molecule or in a polyatomic ion. And that was useful to up to a point. We were able to use that to determine molecular shape, for example, molecular geometry. We incorporated that with differences in electronegativity to look at bond polarity and overall molecular polarity. Um, the Lewis structures and Lewis theory is helpful up to a point. It still doesn't give us any more information, such as about the lengths of bonds, the strengths of bonds, etc. So we have developed and scientists have developed additional theories to help explain some of the characteristics that have been experimentally observed for different molecules and different types of compounds. So the next one we're going to be taking a look at is something called valence bond theory. Okay, and I'll abbreviate this as a VB theory from this point onwards. Okay, and this theory is based on the fact that we are going to treat bonding as when atoms share electrons, which we've already mentioned, but they share electrons when orbitals, atomic orbitals, overlap with each other, right? And that's the key thing when it comes to valence bond theory. Okay, the overlapping of atomic orbitals, right? And we talked a lot about atomic orbitals in the earlier sections. Okay, we're looking here at s orbitals, p orbitals, d orbitals, and f orbitals, for instance. So how does a bond form according to valence bond theory? Well, a bond forms when you have to have single electrons in an atomic orbital, and we have those on two different atoms that overlap with each other, all right? So we need to have one electron present in an orbital, and we need to have another one electron in another orbital, on a different atom. Okay, and these orbitals then have to overlap. Well, first of all, those electrons must have opposite spins. Just remember, our spins could be spin up or it could be spin down. So they can pair up. So there's pairing up that happens when the orbitals overlap. And the reason why, again, that they will want to pair up, why they will want to overlap in the first place is stability. And that stability now is represented by the lowest possible potential energy for the system. Okay, so low potential energy means stable. So if we take a look at a very simple example, the simplest example in the case, for example, of the hydrogen atom and the hydrogen molecule, okay, if I have hydrogen, so if these two are hydrogen atoms, so I have a hydrogen here and another hydrogen, we know H has the electron configuration 1s1. Okay, so if we were to draw the orbital diagram for this, I have the 1s orbital, there's one electron in it. So this here, these spheres represent the 1s orbital. So let's say I have an electron in this one on the left side here, and another one on the right one, and it is an opposite spin. If I bring these atoms, these orbitals close together, eventually they're going to start to overlap. Okay, and as you bring them closer and closer together, that overlapping becomes more extensive until we get to the point where the overlap is such that we have the lowest potential energy for the system. So at this point here, at the bottom of this well, this is the point at which the overlap of the orbitals is optimal. In other words, now what can happen in my molecule when I bring these two H's together is my one electron on one side and the other electron on the other side, they are now shared between both both hydrogen nuclei, right? So the dots there represent the nuclei. So both electrons now are shared between both, and they're shared in the most um, energy stable way, meaning the lowest potential energy. Now you may think, well, what if I just brought them even closer together to increase the overlap? Well, if you try to force them together, what you will see is that the potential energy then increases dramatically, right? So if I bring them together, the potential energy goes up. And the reason for that is now I'm trying to force these protons that are in the nucleus closer to each other. And protons, as you know, are positively charged, right? That's what you have in the nuclei for these hydrogen atoms. So by trying to force those together to increase the overlap, bring them closer together, it actually then becomes less stable. We don't want that. We want the most stable overlap, which is happening right at this depression here, which corresponds to this overlap between the s orbitals in the case of both of these hydrogen atoms. That's the idea behind valence bond. Orbitals overlap. Each orbital has to have an unpaired electron. Those electrons need to be of opposite spin. When they overlap, that's what the covalent bond actually involves. All right, so here's a slightly different example. I mean, well, it's the same example, but the electrons are missing. We'll draw those in. We have one here on the left side. Let's put a red one here on the right. Okay, we bring them together, and then we have both of these now that are shared in this overlapping region between both of these hydrogen atoms, right? So the overlapping of the orbitals is the bond, and that's what valence bond theory involves, right? So this is a s orbital, one s orbital here, which is spherical, as you know, and another one s orbital right next to it. Okay, this is the simplest example. We can apply this to lots of other instances where we have singly occupied orbitals. So in the case of, if you take this one step further, in the case of the fluorine molecule F2, right, if you were to write out the electron configuration for fluorine, right, it's 1s2, 2s2, 2p5, right? So we know that the s orbital, both of the s orbitals are completely filled. When we get to the p orbitals, remember we have three of the p orbitals, the py, the px, and the pz. So let's try to separate this out. Let's say this first one here was the py orbital. We have a pz orbital, and we have the px orbital. Okay, so we have one electron in the px, and I can draw that in right here. So there it is. Okay, all the others have two electrons in them, so they're full. So two there, and then two in the PZ. So the only orbital here that this can potentially bond is the PX with this one unpaired electron. Let's make this the same color. And then in the neighboring F molecule, okay, which has green electrons, well, we have the same thing happening, right? We have two electrons in the PY. We have two electrons in the PZ. And we have one electron here in the px. So when these two p orbitals, when they overlap with each other, we bring these closer together. This is the overlapping region right here. Well, guess what? We have both of these electrons now that are going to be in that overlapping space, in that overlapping region, and that's what the covalent bond is going to be according to valence bond theory. Okay, overlapping of orbitals is what valence bond theory involves. We could also compare that to if you were to now, let's say, mix together, or not mix, but if you were to combine a hydrogen and a fluorine. So hydrogen we know is 1s1, so it's got one electron in its s orbital. It's singly occupied, which is what we want to happen in this situation. In the case of fluorine, as we just mentioned, it is going to have 5 electrons in the p sublevel, so 2 in the, let's say the PZ, 2 in the PY, and then we have 1 here in the PX. when these overlap, right, when the 1s orbital and the p orbital from the F overlap, that forms the bond where we now have two electrons, one from the F fluorine and the other one from the hydrogen that are in that overlapping space between them. We can compare the bond lengths in the hydrogen and the fluorine individually. Hydrogen has a shorter bond length, so it has a higher bond energy than fluorine with a longer bond length, lower energy. The HF bond length is sort of intermediate, and the energy associated with it as well. Okay, so let's take a look at an example. So we have here hydrogen selenide, H2SE is foul smelling, etc. It says the HSEH bond angle in H2SE is approximately 92 degrees. Use valence bond theory to describe the bonding in this molecule. So if you were to draw the Lewis structure for this, okay, we have H, SE, and H. Okay, something like this, and they're telling us the bond angle here is, so bond angle there is, what does it say? 92 degrees. All right, and we're using valence bond theory to explain why that is. Okay, so it gives us or we know what the ground state electron configuration for selenium is Se, 4s2, 3d10, 4p4. So this is what we're concerned with, the valence electrons. So in the case of selenium with 4p4, so this is my selenium atom here, Se, and I have my three of these p orbitals, like so. That's one. Let's say this is my p y. Let's say this is my p. This is the p x, and then my pz kind of in this direction. Okay, so my py. Let's say this is the py. This is the p. Let me rewrite this over on the left side. This is the pz in the other direction. Okay, so let's say the pz, let me make sure I have that right. So the pz is like this, py and the px, right? So we have two electrons in the pz. So there they are, right? That pz can't hold anymore because it's filled with two electrons. The py has one. Draw that, and the px has one as well. I'm going to put this one right here. Okay, and I'll label the px on the other side because it's made up of two lobes. So if I have a hydrogen, because I need two H's, all right? So if I have a hydrogen close by, let's say this is an H, okay, it's going to have an s orbital like this, and I have another H over here with this s orbital, which is spherical. That hydrogen is going to bring an electron. Each of these is going to bring an electron into each of these. So we have, and they're overlapping, which leads to the formation of the bond, right? I'm shading in the overlapping region in both of these. That's the SEH bond in both of these cases. As we know from a few sections before, the angle or these p orbitals are all oriented at 90 degrees to each other. Not Celsius, but just 90 degrees bond angle between them. So what we have occurring, right, is the bond angle here between the PZ, I'm sorry, that would be the PX, sorry, the PX and the PY, right? So the PX and the PY, that is 90 degrees between them. And guess what? The H's are attached at each of these terminal positions, right? So it makes sense that the bond angle is approximately 90 degrees. It's just over 90 degrees. So it does make perfect sense here. Valence bond theory is allowing us to predict the bond angle of this specific molecule.